All right, this will be chapter 4, Helicopter Flying Handbook, page 11 of 18 on an iPad or smart device, going into structural design, 11 of 18. All right. In helicopters with horizontally mounted engines, another purpose of the main rotor transmission is to change the axis of rotation from the horizontal axis of the engine to the vertical axis of the rotor shaft. This is a major difference in the design of the airplane, power plant, and powertrain, whereas the airplane propeller is mounted directly in the crankshaft or to the shaft that is geared to the clutch, that is geared to the crankshaft. The importance of the main rotor RPM translates directly to lift. RPM within normal limits produces adequate lift for normal maneuvering. Therefore, it is imperative not only to know the location of the tachometers, but also to understand the information they provide. If rotor RPM is allowed to go below normal limits, the outcome would be catastrophic. The clutch. In a conventional airplane, the engine and propeller are permanently connected. However, in a helicopter, there is a different relationship between the engine and the rotor. Because of the great weight of the rotor in relation to the power of the engine as compared to the weight of the propeller and the power in an airplane, the rotor must be disconnected from the engine when the starter is engaged. A clutch allows the engine to be started and then gradually pick up the load of the rotor. Freewheeling turbine engines do not require a separate clutch, since the air coupling between the gas-produced turbine and the power takeoff turbine functions as an air clutch for starting purposes. When the engine is started, there is little resistance from the power turbine. This enables the gas-produced turbine to accelerate to normal idle speed without the load of the transmission and rotor systems dragging it down. As the gas pressure increases throughout the power turbine, the rotor blades begin to turn slowly at first and then gradually accelerate to normal operating RPM. On reciprocating and single-shaft turbine engines, a clutch is required to enable engine start. Air or windmilling starts are not possible. The two main types of clutches are the centrifugal clutch and the idler or manual clutch. How the clutch engages the main rotor system during engine start differs between helicopter design, piston power. Helicopters have a means of engaging the clutch manually, just as a manual clutch in an automobile. This may be the means of an electric motor that positions the pulley when the engine is in the proper operating condition, oil temperature and pressure in an appropriate range, but is controlled by a cockpit-mounted switch. Belt drive clutch. But before that, let's see what's going on here. The main rotor transmission reduces engine output RPM to optimum rotor RPM. Okay. Belt drive clutch. So, some helicopters utilize a belt drive to transmit power from the engine to the transmission. The belt drive consists of a lower pulley attached to the engine and an upper pulley attached to the transmission input shaft, a belt or set of V-belts, and some means of applying tension to the belts. The belts fit loosely over the upper and lower pulley when there is no tension on the belts. Some aircraft utilize a clutch for starting. This allows the engine to be started without requiring power to turn the transmission. One advantage this concept has is that without a load on the engine, starting may be accomplished with minimal throttle application. However, caution should be used during starting, since rapid or large throttle inputs may cause overspeed. Once the engine is running, tension on the belts is gradually increased. When the rotor and engine tachometer needles are superimposed, the rotor and the engine are synchronized, and the clutch is then fully engaged. Advantages of this system include vibration isolation, simple maintenance, and the ability to start and warm up the engine without engaging the rotor. When the clutch is not engaged, engines are very easy to overspeed, resulting in costly inspections and maintenance. Power or throttle control is very important in this phase of engine operation. Centrifugal clutch. The centrifugal clutch is made up of an inner assembly and an outer drum. The inner assembly, which is connected to the engine drive shaft, consists of shoes lined with material similar to the automotive brake linings. At lower engine speed, springs hold the shoes in, so there is no contact with the outer drum, which is attached to the transmission input shaft. As engine speed increases, centrifugal force causes the clutch shoes to move outward and begin sliding against outer drum. The transmission input shaft begins to rotate, causing the rotor to turn slowly at first, but increasing as the friction increases between the clutch shoes and transmission drum. As rotor speed increases, the rotor tachometer needle shows an increase by moving toward the engine tachometer needle. When the two needles are superimposed, the engine and the rotor are synchronized, indicating the clutch is fully engaged and there is no further slippage of the clutch shoes. The turbine engine engages the clutch through centrifugal force as stated above. Unless a rotor brake is used to separate the automatic engagement of the main drive shaft and subsequent the main rotor, and the drive shaft turns at the same time as the engine in the inner drum of the freewheeling unit engages gradually to turn the major rotor systems. Alright, so we'll hold off there. That's page 12. That's pretty much the clutches. Yep, the main rotor transmission, the structural design of it, the clutch, a belt drive clutch, and the centrifugal clutch on page 12 in chapter 4. See ya.